Hello, good evening, everyone. We usually have our sessions in Saturday 7 to 9, but I was traveling last week, so we'll have this session today, Monday 7 to 9 p.m. To those who are starting this, if this is your first session, my name is Akhil. I'm currently a PhD student in the Department of Mechanical Engineering at IIT Madras. So I'll be conducting this live samples problem solving sessions for the course Machinery, Fault Diagnosis, and Signal Processing during this semester. Okay. Uh, am I clear and audible? Okay, thank you, Rajesh. So let's begin the session. So this session will mainly cover questions regarding noise measurements and monitoring. So for the first question, what is the sound pressure level and what is the reference sound pressure used while calculating SPL? So there are three different measures of sound called SPL, SWL, and SIL, and each of them have some separate reference values. Based on that, you will tell how much more magnitude or more quantification how the current sound is. So here for SPL, which is sound pressure level. So what is the reference sound pressure which is used when we are calculating the SPL? So SPL is actually 20 log 10 pressure by reference pressure. So the question here is, what is this reference pressure that you need to use when you are calculating the sound pressure level? So any idea, Rajesh? Okay, 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 thank you, Rajesh. So 20 micropascals is the reference pressure that is used while calculating SPL. Okay, so this is something which you need to remember. So 20 micropascals is the reference pressure that is used while calculating the SPL. Okay, so yeah, so let's go to the next question. Now, what is the SPL of sound with a pressure of 1 pascals? So we know the formula for SPL, 20 log 10 P by Pref. So Pref from the last question we know as 20 micropascals, and P here it is given as 1 pascal, right? So now can we calculate SPL? So it is 20 log 10 1 by 20 into 10 power minus 6 pascals. So we are converting this also into pascals. Okay. Now 20 log 10 100 by so 20 log 10 of 5 into 10 power 4. So this would be, you can write it as plus log 10 of 5. So this is 4 plus, so 80 plus 20 log. So this depends on the log 5 value. So this total final value turns out to be around 94 decibels. Okay. So this is how we can calculate the SPL if you know the current pressure based on the reference pressure. So for SPL, reference pressure is always 20 micropascals. So you need to remember that. So whenever you know the current pressure from the by taking the ratio of the current pressure with the reference pressure and then logarithmic and multiplication with 20, you will get the sound pressure level. Okay. Next we will see the other measures. So here the question is SWL of a machine with sound power of 1 milliwatt. So SWL is in terms of power. So for this the formula is 10 logarithmic base 10 W by WRF. So in SPL the multiplication is 20 but in power level it's 10. So that's a major difference which you need to remember. And here we know the power given as 1 milliwatt. What is the reference power? So for the sound power level, the reference power is taken as 10 power minus 12 watt or 1 picowatt. Okay. Now with this, can we calculate the SWL for this? 10 log 10 of W is given as 1 milliwatt and WRF is 10 power minus 12 watt. So 1 milliwatt we can write it as 10 power minus 3 watt by 10 power minus 12 watt. So this is 10 power 9. Yeah. So it's 90 decibels. Okay. So this is how you can calculate the sound power level SWL. So here the only thing to remember is the constant multiplication is with 10 instead of with 20 as the sound pressure level. And WRF is 10 power minus 12 watt. Okay. So that is sound power level. Next we have one more similar quantity called SIL. So SIL is sound intensity level. Okay. So SIL is again 20 log 10 I by IRF, and here IRF is 10 power minus 12 watt per meters. Okay. So here we know sound intensity normal. What is the current sound intensity? 1 milliwatt per meter square, and reference is 10 power minus 12 watt per meter square. So can we calculate the CL? So similar to the last cases, 20 log 10 I here is 1 milliwatt per meter square by 10 power minus 12 watt per meter square. So it comes out as 10 power minus 3 watt per meter square. So 20 into log 10 of 10 power 9, so 180 decibels. Okay. So this is the sound intensity level. So in sound intensity level also use 20 log 10 intensity by reference intensity, and reference intensity is 10 power minus 12 watt per meter square. Okay. So power level you use 10 log 10 power by reference power, and in sound power level the reference power is 10 power minus 12 watt. and the first one is sound pressure level. So here also 20 log 10 pressure by reference pressure, and the reference pressure is 20 micropascals. Okay, so this way now I think you will be able to estimate SPL, SWL, and SIL. Okay, so the next question is, when we add or when two pressures or from two different sources are coming and joining at one point, and each of those pressure levels is 100 decibels, what will be the sum at that point? So let's say you have one source. This source is giving pressure P1 and the other source is giving pressure P2. Now at this point, what will be the resultant SPL? So here one more advantage is both of them are equal. So how can we calculate the sum of these two different pressure levels? Yes. So you are saying SPL equivalent is equal to SPL1 plus SPL2. Okay. So actually that is wrong, because you need to actually go to the fundamental form. In the fundamental form, it is actually a wave propagation, right? Wave propagation, one is from one source and the second one is from two waves are joining there. So if you look at the pressure at that point, at this given point, if only one of them are there, it might be going like this: P1 sin omega t and P2 sin omega t, because due to source 1 and due to source 2. Now at this point, because both of them are there, your um, final would be the sum of these two. So whatever you said sum, you should actually sum these two waves. Okay, not the SPLs directly. So when you sum these two, then the equivalent pressure of these two, because these are sine terms, the effective magnitude for these two curves you can directly estimate like this, right? Okay, so this is the actual pressure equivalent at those 2 points because of P1 and P2. Now you know how is SPL related to the pressure. This is how it is related, right? Now SPL1 will be P1 and correspondingly SPL2 is 20 log 10 P2 by Pref. Now SPL equivalent would be 20 log 10 P equivalent by Pref, right? Now we have P equivalent in terms of P1 and P2, and P1 is in terms of SPL1 and P2 is in terms of SPL2. So we can do some manipulations, which I will show here. So first let's replace P equivalent in terms of SPL, the equation of SPL. So root over P1 square plus P2 square by Pref. Okay, this now, so 20 I am writing it as 2 into 10, and this 2 I am taking to the inside the log, so it becomes power. So next this would actually become the square root and power will get cancelled, and then below PRF there will be a square. Okay, now if I write this, P1 by PRF whole square plus P2 by PRF whole square. Now it is still in terms of P1, P2, but we know from this we can write P1 by PRF as basically, let's take the uh, let's look at it like this. SPL is equal to 20 log 10 P1 by PRF. So here also let's take the 2 inside the log, then this would become 10 log 10 P1 by PRF whole square. Now P1 by PRF whole square can be equated to SPL 1 by 10 into 10 power, right? So I took the 10 to the left hand side and then log also, so it becomes a power, because log 10, so it becomes 10 power, and SPL by 10. Okay, now if you substitute this in this equation for each individual P1 by Pref and P2 by Pref, then you would get SPL equivalent as 10 log 10 of, so P1 by Pref whole square I will replace it with 10 power SPL 1 by 10, and P2 by Pref whole square 10 power SPL 2 by 10. Okay, so this is the final formula when you have two sound pressure levels, or you are adding the two sound pressure levels. Okay, now let's look at what are the SPLs given. In the question we have given SPL1 and SPL2 is equal to, both are equal and same as 100 decibels. Okay, so when they are equal, SPL equivalent, actually it gets even more simplified. So if both are equal, then it would be 10 power SPL by 10 plus 10 power SPL by 10, right? So this would become 2 into 10 power SPL by 10 . So I am writing this 2 into, so separating the 2 and the 10 power SPL 10 by part. So this becomes 10 log 2 base 10 plus 10 into log 10 of 10 power SPL by 10. This is log 10 of 10 power, so this becomes just SPL by 10 and 10 gets cancelled. So SPL plus, so what is log 2 of 10? It's 0.3. So this becomes SPL plus 3. So when you are adding two different pressures or two same pressures, then the equivalent SPL is just the actual SPL plus 3. Okay. So in this question, since SPL is given as 100 decibels, therefore the equivalent SPL would be simple as 100 plus 3 is equal to 103 decibels. 103 is the answer. Okay. Is this clear, Rajesh? Why it is not the direct sum and not 200 answer? So you basically add the pressures and correspondingly the equivalent pressure you will get in terms of the individual pressures. So by based on the pressure and the corresponding SPL relation, we can derive in terms of the equivalent pressure what should be the equivalent SPL, and then we substitute P1 and P2 on the equivalent pressure and then get SPL equivalent in terms of P1 and P2. Okay. From there again, because we are directly given the SPLs of the individual elements, it's better if the final form is in terms of SPL itself. Okay. So to get that, we again substitute back P1 by Pref in terms of SPL. So which will give us this equation. Okay. Yes. Then this formula you need to use if two different SPLs. If both are same, then you can just do like this. If both are exactly same. So I think we have a question where both are different. So that will also come. Okay. If both are different, then we need to use this big formula. If both are same, then because if both are same means 2 into we can write. So that log 2 comes outside and it's basically the normal SPL plus 3. Okay. If both are same, only in that case. Okay. Yeah. Now let's look at the second next question with this case. Again SPL calculation. Yeah. So calculate the sum of two sound pressure levels of 20 and 40 decibels. So we know the formula of SPL equivalent is 10 log 10 power SPL 1 by 10, right, plus 10 power SPL 2 by 10. So this is the formula. Now can you substitute and let me know what should be the answer? So here we are adding two different pressure SPLs as you asked, Rajesh. So SPL1 is 20, SPL22 is 40, right? So this becomes 10 power 20 by 10 2 plus 10 power 40 by 10 4. Okay. Yeah. So if I take 10 power 4 common, so this would be 10 power minus 2 plus 1. So 10 log 10 power 4 into 1.01. So now if you do again, because inside log there is a multiplication. Okay. So 40 plus 10 log 10 of 0.01. So this turns out to be around 40.04 decibels. So you noticed here when we added SPLs of 20 and 40, the final resultant is also almost 40 decibels only. So that SPL of 20 actually didn't add much. So Rajesh, is your doubt clear on how to do this if it is different pressure levels? Okay, okay. Sayali, were you able to follow what was going on with this as you joined late? Okay, so when you have two different pressures joining at a certain point, you can sum up the pressures. So based on that, you will get an equivalent pressure because of the pressures. Each of them will follow a sinusoidal or cos any pattern. The final magnitude would be the sum of root mean square of this, or just the square root of sum of squares, not the root mean square, sorry. Then from that P equivalent, we can write SPL equivalent in terms of individual pressures P1 and P2, and from there again we substitute P1 by Pref and P2 by Pref in terms of their SPLs. Then we will get this final form for the equivalent SPL in terms of the SPL1 and SPL2. And if by chance this SPL1 and 2 are equal, then it's simply whatever existing SPL plus 3 would be the equivalent SPL. Okay. Then we looked at case for with two different SPLs, and let's look at one more question. So calculate the sum of two sound pressure levels of 30 and 32 decibels. So again we need to use the same formula, and I'll give you 2 minutes to solve it. And let me know the answer. Were you able to solve it? So 10 power SPL 1 by 10, so 10 power 3 plus 10 power SPL 2 by 10, so 10 power 3.2. So if you actually substitute this, then you would get a final answer of 34. Yes, exactly. Thank you, Rajesh. So you notice what has happened. So when you added 30 and 32, you actually got 34.12, much higher than the two. But when you added 20 and 40, it stayed same as 40. And when you added both of them same values, then you SPL increased it by 3 decibels. Okay. So from this, what you can understand is, if the decibels are closer, then you will get a maximum change in the equivalent pressure level. If the decibels are very far away, then it will be more closer to the highest decibel. Okay. Like in this case 20 and 40, they are little far away, so the final equivalent is also close to 40, and when they are same, it increases by 3 decibels, and when they are close, if you see 30 and 32, so 34.12 is 2.1 greater than 32, so it's not as high as 3 decibel change, but it's very close. Okay. Yeah, exactly. So you can see that in the equivalent numbers also. Okay. Yeah. So let's go to the next question. An aviating brings down the SPL at frequencies below. Any idea on this? Uh, this aviating is related to what humans can hear and how our eardrums work. So human beings, actually we do not perceive the same pressure level at different frequencies as same. Some frequencies we perceive the same, let's say sound pressure level of 10 as maybe 20, but at frequencies of let's say 1000 or 2000 we may perceive the same sound pressure level of 10 as maybe 5, and our eardrums do not work in linear fashion, and the amplitude also changes how we perceive the sound. So to account for human perception of sounds, there is a weighting method called A weighting, so which reduces the amplitudes for certain frequencies. Okay, so that humans can hear those sounds or identify the differences. So that cutoff is 1000 hertz. So A weighting usually reduces the frequencies below 1000 hertz. Okay. Okay. So that is where A weighting is used, and its cutoff is usually less than 1000 hertz. So anything less than this, they actually reduce the amplitudes. Yes, yeah. In this awaiting, at least you are not accounting for the changing amplitudes effect also on the nonlinearity of the human here. Here only like based on the frequencies, there are some set weights for each frequency. Okay. Next we move into octaves. Okay. If you have come across octaves, then maybe you will be able to answer this question. Which of the following is true for the upper and lower frequencies of a 1 by n octave band? So they are asking how the upper and lower frequencies are related. Any idea? It can be anything. So there are different bands. N equal to 3 is 1 by 3 octave band. N equal to 1 is also possible. Different things are possible. Mainly 1 and 3 are the highly used ones. N equal to 3. So with that given n as the unknown yet, how do you define the upper frequency and lower frequency? How the relationship between these two? Yes, correct. Thank you, Rajesh. So the upper frequency and lower frequency are related like this. So basically what this means is if it is a 1 by 1 octave band, then your Fu is 2 power 1 Fl. Fu is basically 2 times Fl. So this basically means, let's say your cutoff is starts at 20. So for this band, the cutoff would be ending at 40. So this is the band, first band, and again 40 to 80. Okay. So basically one octave band is 20 to 40, 40 to 80, 80 to 160, like this. So this is how the different bands will be there. And if n is 3, then 2 power 1 by 3 FL. So correspondingly the bands will be created. Okay. Okay, I hope this is clear. So the next question, what is the upper frequency, center frequency and bandwidth for a 1 by 1 octave band filter with a lower frequency of 177 Hz? So we were given lower frequency. We need to find the upper frequency, center frequency and bandwidth. Okay. So do you know the relationships between these four in terms of FL and FU? So from the previous question only we have FL and FU, the relationship between them, right? The upper frequency is 2 power 1 by n into the lower frequency. So here we are given 1 by 1 octave band, so n equal to 1. So 2 times FL, so 2 into 177 Hertz. Okay. So now we got the upper band, upper cutoff. Then how are these two related to the FC, center frequency? Any idea? Yes. So the center frequency is actually the square root of the product of the two frequencies. It's not the sum by 2. It's not the average. So the center frequency is actually the uh, square root of FU into FL. So here we have 177 into 354, right? FU and FL. 354 into 177. So this gives something around 250 Hertz, I think, as the center frequency. Okay. So how did this relation came up? So here that's how it is defined actually, square root of FU into FL as the center frequency. Yeah. So next, what is the bandwidth? So what is the bandwidth in a band pass filter? Is just the cutoff difference between the cutoff frequencies. So here FU is 354 minus 177, so 177 Hertz. Okay. So is this question clear? How we can estimate from the lower frequency alone the rest of the parameters, the upper frequency, the center frequency and the bandwidth. Okay. Now let's look at one more similar question. So now what is upper frequency, lower frequency and bandwidth of a 1 by 3 octave filter with center frequency of 1000 Hertz? So now center frequency is given and not lower frequency like earlier question. And we need to find the upper, lower and bandwidth frequencies. Okay. So does anyone know the relation between the upper and lower frequencies with the center frequency? So you can derive from whatever we know till now. So this is how upper and lower are related, right? And we know center is related to upper and lower as the square root of the product. So if you substitute FL as Fu into 2 power minus 1 by n, then let's square on both sides, right? Fu is there 2 times. Now if you do square root again, is that okay? So now Fu will turn out to be Fc. So this is how you can get upper frequency in terms of the center frequency. Similarly, FL would be Fc. Okay. Now let's calculate. So 2 power 1 by n is here it's given 1 by 3 octave band. So 2 power 1 by 6 into center frequency is given as 1000 hertz. And here 2 power minus 1 by 6 into 1000 hertz. Okay. So this is almost 1120 hertz and this is almost 891 hertz. Okay. Now we got the upper and lower frequencies. What about the bandwidth? Is Fu minus Fl. Okay. So here 1122 minus 891 hertz. So almost 231 hertz. Okay. So there is one more direct way to calculate the bandwidth. So that is, let's look here, Fu minus Fl, right? So Fu you can write in terms of center frequency and Fl also in terms of center frequency. So this way you can directly have bandwidth in terms of the center frequencies. Okay, instead of calculating the upper and lower frequencies as we did earlier to calculate the bandwidth, you can directly estimate bandwidth in terms of the center frequencies. Now if n equal to 1, so bandwidth would be 2 power 1 by 2 minus 2 power minus 1 by 2 Fc. So this is actually almost 0.7 Fc. Okay. So for 1 by 1 octave band filter, the bandwidth is almost 70% of the center frequency. And for n equal to 3, it's even less as 0.23 Fc. Okay. So if time is urgent or you need to solve this problem urgently, then you can just use these direct formulas. If you know the center frequency for 1 by 1 octave filter, it's just 70% or 0.7 into center frequency. For 1 by 3 octave filter, it's 0.23 into Fc. Okay. So is this question clear? These three questions relating the upper and lower frequencies to center frequency and the bandwidth and how all these four are related, different relations to remember. So the first one is upper frequency is 2 power 1 by n times the lower frequency, and center frequency is the square root of the product of upper and lower frequencies, and bandwidth is the difference between upper and lower frequencies. Now if you have only the center frequency, then the upper frequency is 2 power 1 by 2n, the center frequency, and lower frequency is 2 power minus 1 by 2n into center frequency, and bandwidth directly you can get it as for 1 by 1 octave filter 0.7 the center frequency, for 1 by 3 octave filter 0.23 of the center frequency. Okay, is this clear regarding this octave bands? Okay, thank you. So let's move to the next question. The audible range for humans is, so any idea on what are the frequencies that we can actually hear? Yes, Rajesh, actually correct, thank you. So we can only hear frequencies between 20 and 20 kilohertz. So if you look at the first option, it says 200 to 2000 hertz only. So the entire band we can hear, but it's not just that, we can hear outside 2000 and lower 200 also. So first option is not correct, and second option is also not correct. You can hear anything between 20 hertz and 20 kilohertz. Okay, but we need to remember that even though sound pressure level might be same when you measure, the sound which you would feel might be different for the different frequencies. Okay, now what are the frequencies of sound less than 20 hertz are called? Basically below the sound frequency which we can hear, what is that sound called? It has a special name. What is that? So sounds less than 20 hertz frequency are called infrasonic. Okay, so any frequency which is less than 20 hertz sound, it's called infrasonic. And ultrasonic refers to the frequencies of range. Any idea on this based on the last question? Yes. So this is ultrasonic. So from 20 hertz to 20,000 hertz, human audible range. So less than this, it's infrasonic, and greater than this, it's ultrasonic. Okay. So 20 hertz to 20,000 hertz is the human audible range, and above that we call them ultrasonic, and below this 20 hertz we call them infrasonic. Okay. Yeah, sorry, I lost my internet for a few seconds. Is the last question clear? Yes, yes. Okay, thank you. So the human audible range is from 20 to 20,000 hertz, and less than that is infrasonic, and greater than that is ultrasonic. Okay. Supersonic is actually when some things are traveling inside some medium greater than the speed of sound in that medium. So it refers to that, not refers to the sound, type of sound. Okay. So let's take some jets which run through air at sounds greater than the speed of sound in air. So speed of sound in air is around 300 meters per second. So if any object is traveling faster than that, then such speeds are called supersonic. Okay. So it's referred to that based on the speed of sound in that matter. Okay. Yeah. So the next question, the region close to the source where the sound level is almost constant and equal to maximum level generated is termed as. So you have a sound source and based on the distance from the sound source there are multiple regions based on how the sound pressure level varies. So what is the region where the sound level is almost constant and equal to maximum level generated? What is that region called? Near field, far field or reverberant region? So when you are very near to the source, then only sound level is almost constant and equal to maximum level generated. So it's called near field region. Okay. So when you are very close to the source with the sound level almost constant and equal to maximum level, that is the near field region. Next question. In the free field region, the sound pressure level reduces by 6 decibels for every dash of the distance from the point spherical source. So let's say we have a spherical source here. In three-dimensional sound are moving away. So very near where the magnitude is same, so that is the near field region, and far away the sound power level actually decreases. So this is the, so away from that it's actually far field region. So in the far field region also there are two layers. So these are walls. So in this far field region, the first part, which is the free field region, here sound pressure reduces gradually as you move away from the source. Okay. So here it reduces by 6 decibels for every how much movement from the spherical source, you will reduce the sound pressure level by 6 decibels. So that is actually doubling the distance. So for every double the distance, let's say this is R from the source and this is 2R. So SPL at R is SPL at 2R plus 6 decibels. Okay, as you moved away to 2R, the SPL reduced by 6 decibels. Okay, because from the point source the sound energy goes in all three dimensions. So the area, the surface area and the same energy is going through higher and higher surface areas as you move away. So because of that the sound pressure level decreases. and for a spherical source it reduces by 6 decibels for every doubling the distance. Okay. Next, here we have a line source. So this is a different type of source than the spherical source. The sound pressure level decreases by how many decibels for every doubling the distance from the source in the free field region. So point source is 3-dimensional, so we lose every 6 decibels, and line source is basically 2-dimensional only. So that's like think of it like this: you are on the traffic, the cars are passing on the road, and you are looking at so these are cars passing on the road, and you are looking at the cylindrical circumferential changes or the radial distance from this traffic point. So there, if you double the distance, you spill it to a spill it. So it reduces by 3 decibels. Okay. So based on the point, so type of source, how much reduction will happen as you double the distance changes. So in a 3D source or a point spherical source, you lose 6 decibels, but in a line source, you lose only 3 decibels. Okay. Is this clear, Rajesh? Okay. Now the region in the far field close to the boundary where strong refractions occur is known as. So basically this last region where the sound will reflect from the walls, and again the sound pressure level doesn't decrease like in free field region because of these walls. So what is this region called? So this is called reverberant region. Okay. So this is the region which is closer to the wall or at the end of the boundary where the sound will reflect, and because of that it doesn't neatly reduce like in the free field region. It could be any value. Okay. Next question. Which of the following field conditions are suitable for noise monitoring? Yeah. So where should you keep your sensors from the machine? Let's say the machine is your source for the noise. Where should you keep it? In the near field region? Yes. Why do you think so? Yes. So when you are very close, the sound levels could be very high, and it won't be feasible to detect neatly. And when you are close to the walls in the reverberant region, you don't know how much to expect because of how the walls are located. But in the far field region, you should expect this, or you can quantify cleanly what should be the magnitude of the sound in terms of decibels. So free field region is the most suitable one to place the sensors for noise monitoring. Okay. So this region suitable for the monitoring. Next question. To obtain free field conditions, special chambers with walls of highly sound absorbing materials are used. What are these chambers called? Echoic chambers, reverberant chamber, none of these. So these are chambers where you try to maintain the entire chamber to be in free field condition. That means even the walls, there is no reverberant condition because the walls absorb all the sound. So what is that chamber called? Exactly. So it's called anechoic chamber. So it's in the name only it's there. There are no echoes. It tries to reduce the echoes. So echoes are actually come from the reflection of the sound. So if your reflections are dead, then it's there will be no echoes. So anechoic chamber. Okay. So there is one more chamber which is exactly the opposite of this anechoic chamber, where you want walls to be highly reflective to the sound. So that is the reverberant chamber. So when you have a reverberant chamber with walls with very reflecting walls, does the sound level decrease with increase in distance from the source? When you have strong reflecting walls in a chamber and you are moving away from the chamber, will the sound level decrease with increase in distance from the source? It doesn't, right? Because of the presence of the walls, the sound might be reflecting back from all the walls. So it could be same magnitude or varying magnitudes everywhere, and it doesn't have to decrease with the increase in distance from the source. Okay. So this is false. The sound levels decrease or increase, it could be anything or it could stay same only with the distance from the source. Okay. Now next question. The cutoff frequency of the anechoic chamber decreases with the in the dimensions of the chamber. So this anechoic chambers, they have certain frequencies above which the anechoic part works, like it becomes a free field region above certain frequencies only. So what is that cutoff frequency above which it can act as an anechoic chamber, and is that related to the dimensions of the chamber? It is related. So this cutoff frequency decreases with the increase in the size. So as you make the chamber bigger and bigger, your cutoff frequency reduces. Okay. This is our last question for this week. Any doubts, Rajesh, on any of the questions which we discussed? Okay, okay, thank you. I'll just revise all the questions once and then we can close this session. So first we begin with calculating or quantifying the pressure levels or the magnitude of the sound. So one of them is sound pressure level, SPL. So this is in terms of reference pressure and the actual sound pressure, and related to them as 20 log 10 P by Pref is the sound pressure level, and for sound pressure level the reference pressure used is 20 micropascals. Okay, and for 1 pascal's pressure we calculated the sound pressure level using this formula, which turned out to be around 94 decibels for 1 pascal. Next we looked at sound power level, which is SWL. So here it is 10 log 10 by of W by WREF, WREF being 10 power minus 12 watt, and the difference is here it is 10 into, not 20 into, and we calculated what is the SWL for a 1 milliwatt source, which turned out to be around 90 decibels. And similarly there is one more measure which is called the sound intensity level. So that again is in terms of 20 log 10 I by IREF, and the reference intensity is 10 power minus 12 watt per meter square. So in SIL 20 log 10 we calculated for 1 milliwatt per meter square, which again came out to be around 180 decibels. Okay, so this is SPL, SWL and SIL. Next we looked at if you have two different sources giving out these pressures or sound waves and they are joining at one point, what would be the equivalent SPL when both are there? So for that we added the pressures and we took the resultant magnitude of the pressures, and from there we related it to the SPL equivalent in terms of the P equivalent, and then SPL equivalent in terms of the individual pressures, and then individual pressures in terms of their SPLs, and after all these substitutions we will get the final SPL in terms of the individual SPLs as this formula. Now if both these SPLs are same, then it simply becomes the SPL plus 3. Okay. Now in this case we looked at two SPLs of 100 decibels are joining, so it becomes 100 plus 3, 103 decibels. Now when you have two different SPLs, then you need to use the full formula 10 log 10 of 10 power SPL 1 by 10 plus 10 power SPL 2 by 10. So with that we can get the effective SPL or the equivalent SPL. So when these two are very drastically different, you see that it is closer to the largest decibel itself. And we also calculate one more where they are different, and when they are 30 and 32 it can go to be around 34. So when the two SPLs actually come closer, then you will bring a larger change than the individual SPLs, and when they are very far away the final SPL is equivalent close to the larger SPL. Okay. Next we looked at the A weighting to account for human inability to recognize all the pressure levels at all the frequencies are same. So A weighting brings down the amplitude at lower frequencies so that they are better audible for humans or better recognizable. So that cutoff is at actually 1000 Hertz. It mainly reduces the amplitudes below 1000 Hertz. Then we looked at different octave bands based on 1 by n octave band and how the upper and lower frequencies for these octave bands are related. So the upper frequency is 2 power 1 by times the lower frequency, where n being the type of octave band. So for 1 by 1 octave band, upper frequency is just the double of the lower frequency. So that means let's say start at 20. The first band would be 20 to 40, second band 40 to 80, third band 80 to 160, go so on. And if it is a 1 by 3 octave band, the upper frequency is 2 power 1 by 3 the lower frequency. Next we looked at only the lower frequency is given and the type of octave band. From that we calculated the upper frequency, center frequency and the bandwidth. So the upper frequency is 2 power 1 by m, the lower frequency, and the center frequency is the square root of the products of the upper and lower frequencies, and bandwidth is just the difference between the upper and lower frequency. In the next question we calculate everything in terms of the center frequency if that is given. So there The upper frequency you can write in terms of center frequency as 2 power 1 by 2n into center frequency, and the lower frequency is 2 power minus 1 by 2n into center frequency. So there we got a direct relation for bandwidth in terms of the center frequency itself. So for if it is 1 by 1 octave band, it's just 70% of the center frequency, but if it is n equal to 3 octave band, it's 0.23 times the center frequency. Next we looked at what is the audible range of for humans, what are the frequencies that are audible, which is 20 Hz to 20 kilohertz, and the frequencies below this audible range are called infrasonic, and above 20 kilohertz are called ultrasonic, and based on the distance from the source and how the sound in that region propagates or goes based on the distance from the source, there are three regions, mainly near field and far field, and in far field there are two more regions, free field and reverberant. So very close to the source where the magnitude or the sound level is same as the maximum output, that is the near field region, and in the far field region the first is the free field region, where the sound level decreases by 6 decibels for every double distance from the source. And there is a third region, reverberant region. Here the sounds reflect from the walls, and because of that the sound pressure doesn't reduce by 6 decibels every double the distance, and it could be anything at the boundaries. So this is the reverberant region. And if it is not a point source and if it's a line source, then the SPL reduces only by 3 decibels for every double the distance. And the next we looked at far field close to boundary where the strong reflections occur, which is the reverberant region. And we saw what are the conditions which are suitable for noise monitoring. So which kind of field conditions, near field or free field or reverberant field? We realized that free field where the sound pressure goes by 6 decibels uniformly for every doubling the distance. So that is more suitable for the monitoring cases. Next we looked at to obtain free field conditions, what are the chambers which are specially made by using absorbing materials as walls. It is called the anechoic chamber. And there are some special chambers also called reverberant chambers where you want very hard reflecting walls. So there the sound actually doesn't decrease with increasing distance from the source. And we looked at these anechoic chambers have some certain cutoff frequencies above which this sound gets absorbed by the walls, and you will have that neat free field region. So this cutoff frequency actually decreases with increasing the dimensions of the chamber. So as you keep increasing the dimensions of the chamber, your cutoff frequency decreases. Okay, that is it for this week. We'll meet again on Saturday only, not on Monday. Saturday 7 to 9 p.m. next week. Okay. Thank you, Rajesh.